Well, hello, hello. Here we go. So first day was arithmetic. Second day is geometric. All right. So what we're going to look at today is instead of adding the same thing every time, we are going to be multiplying by the same number every time. So this right here is going to be considered our common ratio. Boom. And this, I'm really trying to train you to look at this and not read u sub n plus 1 over u sub n. What I want you to say is, I take any two consecutive terms and find the ratio. So if I take one number divided by the number in front of it, any two in that sequence, I always get the same ratio. So that's kind of the definition of what we call a geometric sequence. Any two. So, for example, 2, 10, 50, 250 is certainly a geometric because it satisfies the idea that if I take 10 over 2, so this term over this term, and that's going to be the same thing as these two consecutive terms, which is the same thing as these two consecutive terms, which always equals 5 in this case. So that's not what, when you look at a sequence that's geometric, you're thinking to yourself, hey, it looks like I multiplied by 5. And you're right. But how did you get multiplied by 5? Because you took 10 divided by 2. Yeah, I know. You want to say, oh, I took 2 times what equals 10. That works too. But just be careful. Is this a geometric sequence? Well, let's check our little model. Negative 10 divided by 2, is that the same thing as 50 divided by negative 10? Is that the same thing as negative 250 divided by 50? Yep, they're all equal to negative 5. Okay, so that means that is also a geometric sequence. Kind of cool that they can flip like that. So yesterday we talked about what if we have terms A, B, and C. If they are an arithmetic, then B turns out to be what we call the arithmetic mean. And we could take A plus C and divide by 2. That doesn't, in a geometric, if it's geometric, then we take B divided by A should always be equal to C over B, the ratio of consecutive terms. Well, let's just work this out and see what happens. I get B squared is equal to AC, and B equals plus or minus the square root of AC. All right, plus or minus, because when we take the square root, we have to do plus or minus. So let's do a quick example. This is 2. We don't know, and this is 18. Yesterday, I said, what's the arithmetic mean? And you said, come on, add them, divide by 2. And you gave me 10, and that was an arithmetic mean. Worked out perfect. Here, we want what is the number here so that this is in a geometric sequence. Well, that is going to be called the geometric mean. And what we do is we say that is equal to plus or minus the square root of 2 times 18. Which is plus or minus square root of 36, which is equal to plus or minus 6. So in your head, let's think about it. Yep, looks like I'm multiplying by 3, multiplying by 3. Beautiful. Multiplying by negative 3, multiplying by negative 3. They both work. Awesome. You geometry buffs, do you remember this? That length is the geometric mean. Between that, kind of cool. So if you have a right triangle and you know this length and this length, that height is the geometric mean of those that hypotenuse. Pretty cool. All right, general term formula. Well, all right, let's take our 2, our 6, our 18, our 54. Let's stop there because I don't want to multiply anymore. All right, so that is a geometric. I'm looking at it, I see 3. If I want to find this next term, or actually let's talk about this. If I went from here to here, I multiply by 3. If I go from here to here, I multiply by 3. So basically, to find the second term, I started with the first term and multiplied by r. That's great, Mr. Sayers. To find the third term, I start with the first term and I multiplied it by 3 once and twice. So it's r squared. To get to the fourth term, and so forth and so on. So a lot like yesterday, we're looking for patterns. To get to any term, I start with the first term, I multiply it by r n minus 1 times to get to the nth term. So if I wanted to find the 25th term, I would start with the first term and I'd multiply that by r 24 times. 24 times. That would give me that 25th term. That's it. All right. So in general, we have a first term, a constant ratio r, and we have our equation. Yesterday I tried to set you up with your notes, and we have this little nice general way. All we're going to be doing is the general term and the summations. Summations we'll get there in a couple days, but right now we should have two equations. All right, our first example. So consider the sequence. Is it arithmetic or geometric? Oh, Sayers, come on, we're talking about geometric, but I want to train you when you're looking at an equation or a sequence, you should ask yourself, is it arithmetic, geometric, or neither? We have tools for arithmetic and geometric. If it's neither, then you just leave it alone, or you kind of do what you can, but you don't panic. All right, so here we are with our good friend A, and show the sequence is geometric. So show, once again, is not going to just be like, oh, it looks like you're multiplying by 1/2. Yeah, that's because you're smart. So what we're going to do is take any two consecutive terms and show that no matter what I do. So I take 8 and 4. Oh, no, I don't. No, I don't. No. Come on now. I could argue it, but I want to be consistent. So what I want is 4 over 8. And ask myself, is that the same thing as 2 over 4? Is that the same thing as 1 over 2? Is that the same thing as 1/2 over 1? And you bet they all equal 1/2. That is my constant ratio. All right. Part B is asking very nicely, what is the nth term? So since this is geometric, I write down my formula. And the two things that I need to find are r and u sub 1. I leave n in the formula because that's our variable. That's where we can plug in what we want. This is pretty straightforward. The first term is 8 times 1/2 to the n minus 1. Will the book disguise that answer? Absolutely. So once again, do not freak out. I don't want you to. I want you to leave it just like that so I can see exactly what you're connecting, but I will just show you. They might do something like this. Which is equal to multiplying exponents, and finally you can add those. So believe it or not, if I plug n equal to, if I want to find the fifth term, I can do it this way, or I can do it this way. Both should work. Both should give me the right answer. And it looks like I get 1/2. Is that the fifth term? It is. All right, so hence find the 12th term as a fraction. So C as a fraction, I'm going to use what I told you that I think is best. The 12th term, 8 1/2 times 12 minus 1. That is 2 cubed times 1/2 to the 11th. And that is going to be 1 over, that's 2 to the 8th. I would leave it like that. Some of you guys, I believe that's 256. Oh, maybe. I think that's right. 256, 248, 1632, 64, 128, 256. Bam. All right. Fingers come in handy. So there's your first half of the homework. State the use in the one. Okay, I think we can. All right, so here we are. We're given three terms, A, B, and a C, and we're asked to find what values of K so that when I plug it in, I get three numbers that are in an arithmetic sequence. So the definition of a geometric is the ratio of any two consecutive terms always has to be the same. So I'm going to set those two equal and then go for it, right? So I get 2k squared is equal to 21 minus k times k minus 1. 4k squared is equal to 21k minus 21 minus k squared and plus k. All right, so let's get it all over this side. I get 5k squared, oh man, minus 22k plus 21 equal to 0. All right, you factor amazing people out there. I wish I could get a little bit of help virtually. I know that has to be true if it's going to work out nice. So let's see this bad boy. Maybe 3 and 7. Maybe 3 and 7. So 3 and 7, 3 and 7. I see 7, I see 15. Woo! That was pretty lucky. So that is going to give me k equal to 7/5 and k equal to 3. I'm going to check the difficult one, 3. So let's plug it in. I get 3 minus 1 is 2. 2 times 3 is 6. And 21 minus 3 is 18. That totally works. So by default, 7/5 has to work, right? I'll leave that one up to you to check out. All right. Okay, here we are. We're just like the arithmetic. We're given two random terms. You know, the picture sometimes is worth a little bit. Here's a bunch of numbers. We know the second term is -6. And we know the fifth term is 162. All right, kind of there's that general way that I can look at it and kind of fix this problem, and then there's the one that works, a method that always works. So I'll give you kind of both. The u sub 2 equals -6. That translates into the equation -6 equals u1 r to the first. Okay, so I'm using our formula u sub n equals u sub 1 r to the n minus 1. So I know the second term is -6. I don't know the first term. I don't know the constant ratio, but I plug in, I'll just write it 2 minus 1 there so you can see it. The next one is u to the fifth equals 162. So I write 162 is equal to u to the 1 r to the 5 minus 1. All right, a lot of different ways to solve this. I'm going to clean that up a little bit and write it as u sub 1 r to the first equals -6. And I'm going to write u sub 1 r to the fourth equals 162. All right, this is the way the book does it, and I thought it was kind of cool, is they stack them like that. What they do is they say, since this equals this, then I can just divide both, make that into one equation. So they write it as u1 r to the first over u1 r to the fourth equals -6 over 162. Very cool. U sub 1's cancel. R to the first goes to r cubed. So with a little bit of manipulation, we get r cubed equals 162 over negative 6. And that gives us r cubed is equal to negative 27. Cubed root of negative 27 is negative 3. Hey, we're trying to find the general term. That means we need to find the first term and r. We already have r. We're going to plug that in and get the first term. Or maybe just look at the second term. Instead of multiplying by negative 3, I would probably divide by negative 3 to go backwards. So I'll leave that one up to you. The homework, as you can see, certainly they give you two terms and you can walk through that. All right, that, ladies and gentlemen, I think we can do that. All right, growth and decay. Whoa, no, whole another section? Nope, it is the same thing. So look at this growth and decay model that they give you. It sure looks a lot like u sub n equals u sub 1 r to the n minus 1. I would just pay attention to the exponent and say, does it relate to the problem? If I plug in a 1, what am I finding? The amount after 1 year or the starting amount, stuff like that. So just be careful. Just be careful. Let's just do a problem and see how you walk through this. All right, we got some wabbits, wascally wabbits on a farm. We got 50 of them, so that's our starting amount. They increased by 7%. All right, so let's find our model. Hey, you know what? Our model is going to look a lot like u sub n equals our starting amount, 50, times 1. Why 1? Because 1, we're either going to increase or decrease. So we start at 1. We're increasing by 7% per week. So let's just try it. If I plug in 0, 1.07, if I plug in 0 here, I get that to the 1, I get 50. Isn't that our initial amount of 50? So at 15 weeks, all we have to do is plug in 15 for n. So what does that look like? U sub 15, or after the 15th week, 51.07 to the 15th. That is good living. Okay. Hey, part B though, this is why we do logarithms. Okay, it says how long will it take to get to 500? So we just set 500 equals 50 times 1.07 to the, sometimes people use t here instead because it's time, but we'll just use our n. Divide by 50. And go look at your logarithm test, and you guys all did so well, I'm pretty darn sure that you can solve that from there. All right, that is it. That's all I have. All these are basically the same. I'd love to have some questions. Good luck.